This is EE698I, mixed signal IC design. And this is lecture number 11. In the last couple of classes, we have been discussing about the possible implementations of the sampling switch. And we noticed that we have 4 possible options in front of us. Right, so the first option is to use the NMOS switch. And we can use the NMOS switch in cases where we need to pass constant input voltage that is close to 0 or some low input voltage. We also have the PMOS switch, which can be used in scenarios where we need to pass constant input voltage close to VDD or some high input voltage. We also have the CMOS switch, also called the transmission gate switch, which is essentially a parallel combination of the PMOS and the NMOS switch. And we can use it in cases where we need to pass constant input voltage ranging all the way from 0 to VDD. And in the last class, we saw that if we have to sample a continuously time varying signal to ensure sufficient linearity, we will have to use the gate bootstrapped switch, where the idea is to make sure that the transistor operates with a constant gate to source voltage of VDD. So I'll simply represent it by showing a capacitor like this. And this can be used to sample time varying Vin, again ranging all the way from 0 to VDD. Okay. And please note that, this gate bootstrap switch can be used in any of these cases as well, but it will simply be an overkill, right? Because if we are trying to sample voltages that are constant or some held input voltage, either of these 3 will suffice, right? And again, a transmission gate can also be used in place of an NMOS or a PMOS. But the point is that if the input voltage is close to 0, even if you use a transmission gate, the PMOS switch will offer a high resistance and it will be finally dominated only by the NMOS switch, right? We also know that for all these switches, the on resistance is inversely proportional to W by L. So to have the lowest on resistance, we need to choose the length to be the minimum possible length allowed in the process. And we can vary the width of the transistor to get the desired on resistance. Okay. So this is about the finite on resistance part. So now let's start to discuss about the other non-ideality, which is the noise. Okay, so let's say this is my switch here that is trying to sample some input voltage Vin. And this switch here can be any of the 4 possible options we discussed. Say this is my sampling capacitor. And let us say that I apply the correct gate voltage to turn the switch on. So if this is Vout, we know that ideally when the switch is on, Vout is equal to Vin. So which means if I make the input 0 and if I turn the switch on, ideally Vout must be equal to 0. But it turns out that in practice, if you measure this output voltage, it will show some small fluctuations around Vin. And this is due to the random motion of the electrons in the channel when the MOSFET is turned on. Because of this random motion of the electrons, we have a non-zero current flowing, and this will result in a non-zero output voltage. And this random motion of the electrons is due to the thermal energy that the electrons possess. So this is also called the random noise or the thermal noise. Not just with this MOSFET, even if you take a simple resistor like this, if you try to measure the voltage across this resistor accurately without adding any other non-ideality to the measuring setup. So if I call the voltage VR, ideally we expect that VR should be equal to 0, right? But again, due to the random motion of the electrons here, we will have some small fluctuations like this. Okay, this is again due to this thermal noise. And it turns out that this thermal noise is a stationary random noise. And to characterize it, we need the statistical properties, which are the mean and the autocorrelation. And the mean of this noise is 0. This should not be surprising, because if the mean of this voltage noise is indeed non-zero, what does it mean? Well, you can take the resistor, and if you just measure the voltage across it, it's a non-zero DC voltage. So I can hook up a resistor and use it as a power supply, right? Or put multiple resistors in series and use it as a power supply. But of course, that is not possible, right? That doesn't happen. So which means the mean must be equal to 0. Second, the autocorrelation function, I'll just call Rp of tau, turns out to be a delta function that is an impulse function, and the area of that impulse is 2 kTr. So if I plot the autocorrelation function, there will be an impulse at tau equal to 0, and the area of the impulse is 2 kTr. So what does that mean? It means that the voltage at any particular time instant has no relation to voltages at any other time instant. Okay, so this noise is called the uncorrelated noise. And if you look at the power spectral density, which is defined as the Fourier transform of this autocorrelation function, the two-sided power spectral density will be flat, right? So this is F, this is say SV of F. It will be constant and equal to 2 kTr. So this is the two-sided PSD. Similarly, if you look at the single-sided power spectral density, it will be flat and the value is 4 kTr. Okay. So the single-sided power spectral density is 4 kTr whole square per hertz. Okay, so please recollect that this is just the spectral density. So what it really says is the power measured in a 1 hertz bandwidth, right? So since here we have a flat power spectral density, 4 kTr, if you measure the power of the signal in any 1 hertz bandwidth, it is equal to 4 kTr. Okay, so the other way to think is that if you take this resistor, connect it to a bandpass filter with a bandwidth of 1 hertz, irrespective of the center frequency, if you look at the power of the output signal, it is going to be 4 kTr, right? So if we call, say, V0, the mean square value will be 4 kTr, right? Because the power spectral density is flat and equal to 4 kTr. Okay. So the way to model this noise is as follows. So here we have this resistor, which is noisy, right? So let's say I call these terminals A and B. So what we can do is we can model it by having a noiseless resistor like this. And in series, we have a voltage source Vn that models this random noise. Okay. So this will be my terminals A and B. And remember that the resistor values are, and this resistor is noiseless. Okay. And as we saw, the power spectral density, the single-sided power spectral density of this noise is 4 kTr, right? Volt square per hertz. So we can also model this in another way by doing a simple source transformation, by converting this voltage source in series with the resistor to a current source in parallel with the resistor, right? So this is the noise current source. And then we have the noiseless resistor like this. And these are my terminals A and B. Okay, so if I call the noise current as IN, how is the noise current IN related to the voltage VN? It is simply VN by R, right? So if I take the power spectral density of this noise current, how will it look like? SIN of F will be SVN of F divided by R square, right? Because we are dealing with power now. So SIN of F is what? 4 kT R by R square, which is simply 4 kT by R, right? Ampere square per hertz. Okay. So in our sampling circuit, what do we have? If we don't have the input voltage, so we have the switch here, which has this on resistance, and we are trying to sample this voltage, right? So again, due to the noise generated by this resistor, the voltage across the capacitor will not be equal to 0. And what we are interested in is to know the statistical properties of this sampled noise signal. Okay, so how to model this? So this noisy resistor, we'll replace it by this model, right? We can use either of the two. But since we have things in series here, we'll use the voltage source representation. Okay, so this is V. And please notice that the polarity of this voltage source does not make a difference because we are only interested in the statistical properties, and also the mean is 0, right? So the polarity of this voltage source doesn't matter. So this is my R, this is my C. Okay, so we are interested in the statistical properties of this voltage, output samples, right? So before going into this, first let's look at some simpler circuit, which is this, right? So let's not have the switch. We'll just say that we have this noisy resistor connected to the capacitor, right? So let me just redraw it by putting the voltage source here. Okay, so this is my noise voltage source, the noiseless resistor R, and the capacitor C. So now let's try to find out how will V out of T, that is V naught of T, look like. Okay, again, we are interested in finding both the mean and the power spectral density. Okay, so what is the mean of the signal? Well, notice that the input has 0 mean, right? So the noise, as we discussed, has 0 mean. And since we are giving this to an RC circuit, the output must also have 0 mean, right? Because mean is nothing. So if this input signal to an RC filter has 0 DC, and if the capacitor has initially no charge, then the output DC must also be 0, right? So the mean of the output signal must also be 0. Okay. Well, as a side question, please think about this. Is it true that if I give a signal x of t, which has average of 0, is it true that if I give it to any system and I get output y of t, will the average of y of t be 0? That is, if I give a signal with a 0 DC input to any system Will the output average be 0? Or can you think of an example where the input has 0 DC component? I give it to some system, but the output has a non-zero DC component. Okay, so think about this. We'll discuss in the discussion session. So now getting back to the problem at hand. So we now found the mean to be 0. Now we are interested in finding the power spectral density and the mean squared of this output voltage. So the mean squared value or the power is nothing but the integral of the power spectral density. So first we need to find what is this power spectral density of V of t, V naught of t. Okay, so we have this circuit Vn, R, and C. Right? We know that the input power spectral density, that is the power spectral density of Vn, is 4 kTr, right? The single-sided power spectral density. And this is going to a filter. This can be thought of as a filter, right? And what is the transfer function of this filter? H of f, it is simply 1 by 1 plus j 2 pi f RC, right? So we know that the output power spectral density, so if I call this as output, S V naught of f is the input power spectral density times mod h of f square. So this is simply equal to 4 kTr by 1 plus 4 pi square h square r square c square. Okay, so this is the output power spectral density. So from this we can calculate what is the mean squared value of V naught, right? What is that equal to? This is simply equal to the integral of the power spectral density, right? So this is 0 to infinity 4 kTr by 1 plus 4 pi square h squared r squared c squared df. And I can simplify it further like this. So I'll take 4 kTr integral. So denominator I have 2 pi frc whole squared. So I'll try to make the numerator also to be of that form. So I will just say it's d of 2 pi frc. So since I'm multiplying 2 pi rc extra, I'll just divide it here. 2 pi rc divided by 1 plus 2 pi frc the whole square, right? And since f is going from 0 to infinity, even 2 pi frc will go from 0 to infinity. There is no change in the integral limit. And you know, dx by 1 plus x square, if you integrate it, we get tan inverse x, right? So this is simply equal to 4 kTr by 2 pi rc tan inverse of 2 pi frc. And we need to take the limits from 0 to infinity. So this is equal to 4 kTr by 2 pi rc. So when we put infinity, we get tan inverse of infinity, which is simply pi by 2. And when f is 0, I mean when this quantity is 0, tan inverse of 0 is 0. So I just get pi by 2, right? So this simplifies to 4 kTr by 2 pi rc into pi by 2. So this pi goes off. 2 times 2 cancels with 4 and r gets cancelled, right? So finally we end up with kt by c. Okay, so what does this say? Well, if you take a resistor here, again this is the noisy resistor, that is the real resistor, connected to a capacitor here. If I measure the mean squared of this output voltage, that is the power of this output voltage, that will be equal to KT by C. Okay, so let's see if this result makes sense. So first, we notice that it depends on the temperature T. And this makes sense because the random motion of the electrons is in turn due to the temperature, right? So this is fine. But surprisingly, we notice that it seems to depend only on the capacitor and it is independent of this resistor value, right? Because to begin with, if you recollect, this noise is coming only due to the resistor, right? But if you look at the the mean squared value, it seems to be independent of the resistor, and the poor capacitor it's looking like the capacitor is taking all the blame for the noise. So what do you think is happening? So please pause the video and think about it. So what's happening is the following. If you look at the power spectral density of the output, that is this guy, this guy. So it is 4 kTr by 1 plus 4 pi squared h squared r squared c squared. Right. So if you try to plot it, what happens? So I just plot the single-sided spectral density. This is my f. This is SB naught of f. So it's going to start from 4 kTr, right? And then it will do something like this. So let me draw it like this. Okay. And this might be my cutoff frequency 1 by 2 pi RC. Okay. And what is this mean squared value? It is the entire area under this curve, right? So now let us say I change the resistor value and let us say I reduce the resistance value. So what will happen? If I reduce the resistance value, notice that this is 4 kTr. So if I reduce the resistance value, this point will also change, right? But similarly, this cutoff frequency will also now increase, right? So I'll get some curve like this, right? And similarly, if you increase the resistor, this portion will increase, but the cutoff frequency will decrease, right? So you might get some curve like this. Okay. So overall, even if the resistance varies, the entire area under the curve will remain constant because when you change the resistance value, both the power spectral density value changes and the bandwidth of the filter also changes. Okay, so these two effects exactly cancel each other. And finally, the mean squared value is simply equal to KT by C, right? So if you increase resistor, both the PSD will increase. But what happens? The bandwidth will decrease, right? So because of this, the mean squared value is independent of the resistance value. Okay. So there is another way in which you can derive the result, that is using what is known as the equipartition theorem. So you might be familiar with this from thermodynamics, right? So what it says, if a system is in thermal equilibrium, each degree of freedom has an average energy of kT by 2, right? And in this RC circuit, there is only one degree of freedom that can store energy, that is the capacitor. And what is the energy stored in the capacitor? It is half C times V naught squared, right? So which means what is the mean squared value? It's KT by C, right? So in a similar way, we can also show that even if you have a second order RC filter like this, so let's say if it's R1, C1, R2, and C2, and again, all these resistors generate their own noise, right? So the power spectral density of the noise due to this resistor will be 4 kTr1, due to this will be 4 kTr2. And if you try to find the mean squared value of the voltage across this capacitor C1, that will turn out to be KT by C1. Similarly, for this capacitor, it will turn out to be KT by C2. Okay, so in general, across any capacitor, the result will be KT by C, right? And this will be fine as long as you don't have any poles at the origin. Okay, and a more general result is the following, where the mean squared value, okay, across, let us say you have a network comprising only of R, L, and C. Of course, R will generate noise here. So if you look at the mean squared value across any two nodes, that will depend, that will be equal to this KT times limit S tends to infinity, S times Z naught of S minus this aside, limit S tends to 0, S times Z naught of S. Okay, so where Z naught is the impedance looking into this port. Okay, this can in turn be simplified like this. It is KT times 1 by C infinity minus 1 by C naught, where C infinity is the capacitance looking into that port. When you make both all the resistors and the inductors, when you make them to be infinite and open circuit them. Similarly, C naught is the capacitance looking into the port. Then you make sure that all the resistors and the inductors are all short circuit. So here they tend to infinity, here they tend to 0. Okay. Well, this comes from this because if you look at S times some Z of S, some impedance, for a resistor it is S times R, right? For an inductor it is S square L. For a capacitor it is S times 1 by SC, it is simply 1 by C. Okay. So if you tend S to infinity, what happens? The resistance and the inductance, they go to infinity, right? And only capacitance remains. Similarly, when you make S to 0, both resistor and the inductor tend to 0, right? So it's equivalent to replacing them with short circuit. Okay. So, and if you want to learn more about this, you can search about this Bode's noise theorem. In fact, this result comes from this Bode's noise theorem. And if you want to read more about this, you can refer to this paper by Professor Shanti Pawan. Okay. So the bottom line of all the discussions is this. So if you take any RC circuit like this, okay, this is R and this is C. If I call this as V naught of T, the power or the mean squared value of V naught is simply equal to KT by C. Okay. But the actual circuit we are interested in is the following, where we also have a switch here. Right? And what we are interested are the samples V naught of M. Okay. So what happens when the switch closes? The noise generated by the resistor will induce some voltage across the capacitor. And the moment the switch opens, the capacitor samples and stores that noise that is sampled on the capacitor. Okay. So let us say this is the clock signal controlling the switch. And let us say this is the instant, say n-1 TS sampling instant. And this is the sampling instant, that is n times TS. Okay, so during this phase, the switch is turned on. So the equivalent circuit will look something like this. The switch is on. I have R, I have C. Again, I'll replace the noisy resistor by a noiseless resistor in series with the voltage source. Okay, this is R and this is. And please notice that in the previous time instant, that is n-1 TS, the capacitor would have sampled some noise, right? So let's call that noise sample to be V naught of n minus 1. Okay, so the capacitor has this initial voltage, right? So when you turn the switch on like this during this phase, two things happen simultaneously. One, the initial voltage, that is the noise sampled in the previous phase, it starts to decay, right? And it decays with the time constant RC. Secondly, this noise source Vn tries to charge the capacitor to some other voltage, right? So second is Vn charges the capacitor, right? And if you notice, if you recollect from your basic classes, this V naught of n, how does it decay? It will decay like this, right? Exponentially, it will decay like this. And the time constant again is RC. Okay. And what do we do to this time constant RC? In general, we make sure that this time constant is much smaller than the time available for settling, right? Only then the signal or the switch can track the input, right? So since we ensure RC to be much less than Ts by 2, the initial condition, that is V naught of n minus 1, will quickly decay to 0. So at the end of this phase, that is at this point, when you try to take the sample of this capacitor voltage, that is V naught of n, that will have no contribution from V naught of n minus 1. Okay, so V naught of n is completely uncorrelated to V naught of n minus 1 and other previous noise samples. Okay, so this is one observation we can quickly make, right? Since the noise samples V naught of n are uncorrelated, what will happen? If you look at the power spectral density, it will be flat. So the noise samples will correspond to a white noise sequence, right? So if you look at the discrete time power spectral density from 0 to pi, I'm showing only one-sided again, it's going to be flat. Okay. So please remember that the continuous time noise, that is V naught of t, that is not a white noise sequence, and that in turn has a shape like this. Okay. But the moment you sample this noise, V naught of t, to get the samples V naught of n, and if you choose the RC time constant to be much smaller than Ts by 2, the noise samples will be white, and the sampled noise will have a flat spectrum like this. Okay. So we know that for the continuous time noise, the mean squared value was kT by c, right? So what will be the mean squared value of the sample noise? Well, it will also be same, right? It will also be same as kT by c, right? Because we are obtaining this by simply sampling the sequence. Okay. Well, the other way to visualize this result is as follows. Well, we know that the power spectral density of V naught of t is going to look like this. Yes, V naught of f. So how is it going to look like? So I'll show the two-sided spectral density. So it will look something like this. Oops. Again, this should be an even spectrum like this. Okay. The moment we sample V naught of t to get V naught of n, we know that when you sample a signal in the time domain, we'll expect some kind of periodic repetitions in the frequency domain, right? So this is my power spectral density for the continuous time signal. And let's say this is my RC bandwidth. Okay. So when you sample this signal to get V naught of n, what will happen? This portion of the spectrum will get repeated around multiples of fs. right? And please note that we choose RC to be much smaller than TS by 2. So which means that the RC bandwidth and the sampling rate. Okay. So what will happen because of that? Let's say this is my FS. So the spectrum will get shifted to the left like this. Sorry, shifted to the right like this. Similarly, we'll have one more copy like this, right? Shifted to the left. And again, we'll have more copies shifted around multiples of FS. Okay. And because of all these copies, from 0 to FS, if you look at the spectrum, now all the portions of the spectrum will get added and we'll get a flat portion for the spectral density. Okay, so from 0 to Fs, which is similar to 0 to 2 pi in discrete time frequency, the power spectral density is going to be flat. Okay, and what is the mean squared value of the discrete time noise samples? It is going to be the area under this curve, right? This area. And note that this area is getting contributed by this entire portion of the curve, because we notice that because of this periodic repetitions in the spectrum, this entire portion of the spectrum will get aliased back from 0 to 0 to Fs. Okay, so because of that, if you look at the total area of this portion, it will be same as the total area under this curve. Okay, so to add more clarity, let's look at a simplified example. So let us say this is the spectrum, the power spectral density of V naught of T. So this is V naught of F. And let's say it is simplified like this. So let's say this is Fs, this is 2Fs, and this is 3Fs. This is minus Fs, minus 2Fs, and minus 3Fs. Okay. We know that the mean squared value of V naught of T is KT by C. And this is essentially equal to the total area of this curve, right? And if I say that the area of this portion is A1, this portion is A2, and this triangular portion to be A3, I'll have same the negative frequency side also. So the total area is 2 times A1 plus A2 plus A3. Okay. So now if I sample V naught of T to get V naught of N, what will happen to the spectrum? We will have periodic repetitions, right? And we'll consider only the spectrum from 0 to Fs, that is the two-sided power spectral density, right? From 0 to 2 pi. Okay, and the mean squared value or the power of the sampled noise will simply be equal to the area of the power spectral density between 0 to Fs. Okay. So now we know that when we sample, the power spectral density will be repeated around multiples of Fs. So we'll have repetitions around kFs, right? So if I say for k equal to 0, we'll get back the original spectrum like this. So let me draw that first. Oops. Okay. So let me push Fs here. This is Fs. This is 2Fs. This is 2Fs. This is 3Fs. Similarly, minus Fs, minus 2Fs, minus 3Fs. Okay. So now if you look at this range alone, from 0 to Fs, the area we have now here is only due to this A1, right? So the area is now due to A1. So now let us say I shift the spectrum to the right by Fs, that is for k equal to 1. What will happen? This spectrum is going to get shifted to the right by Fs. So this portion of the spectrum from minus Fs to 0 will now get alias to this point, right? So now we'll have something like this. Okay. So the area now getting added to this range is this A1, right? So we'll have A1 here. Similarly, if you shift the spectrum to the right by 2Fs, that is corresponds to k equal to 2, that is corresponding to k equal to 2, what will happen? This portion from minus 2Fs to minus Fs, this guy, it will get shifted here, right? And this will alias it. Okay. So now the area getting added will be A2. Similarly, if you shift it to the right by 3Fs corresponding to k equal to 3, so this triangular spectrum from minus 3Fs to minus 2Fs, that will get aliased, right? So this area will get added here. So we'll have the area A3 getting added. Okay. Now the moment you put k equal to 4, that is, we are shifting the spectrum to the right by 4 times Fs, what will happen? So the starting point here is minus 3Fs. That will now be minus 3Fs plus 4Fs, that is Fs. So it will start like this now. Okay. And we clearly see that there is no contribution made to this portion, okay, from 0 to Fs. So we don't have to consider other values of k beyond 3. Okay. So now we need to also take negative values of k, right? So what will happen if I put k equal to minus 1? So let me shift this up. So if I put k equal to minus 1, the spectrum will get shifted to the left, right? So in that case, this portion from Fs to 2Fs, that will get shifted to the left and will add to the area. So we'll have A2 here. So similarly, if you do minus 2, this portion from Fs 2Fs to 3Fs, that will get added here. So we'll have the area A3 getting added, right? And again, if you put k equal to minus 3, what will happen? 3Fs is here. So we are shifting to the left by 3Fs. So we'll have something like this. And we'll have no contribution in this frequency range. Okay, so we don't have to consider anything beyond k equal to minus 2, right? So now what is the total area that is getting aliased in this frequency range from 0 to Fs? Well, that's simply twice A1 plus A2 plus A3, right? And we know that this is simply equal to KT by C. Okay. So the bottom line is that when we have a scenario like this, where we have this noisy resistor and we have this as V0 of t, the mean squared value of this continuous time noise is KT by C. Okay. And the power spectral density is some kind of filtered power spectral density like this. Okay. And when you have a sampling network like this, where you periodically open and close the switch, and you take the samples of this noise, the mean squared value of this samples will also be equal to KT by C, but the samples of this noise will have a wide power spectral density. Okay, so if you look at the discrete time power spectral density from minus pi to pi, or say from 0 to 2 pi, anything, it's going to be flat. Okay. So let's stop here and continue from the next class.